Welcome, fellow cosmic explorers, to another captivating episode of The Cosmic Commute. Today, we embark on a celestial journey to uncover the mesmerizing tales of cosmic birth, the formation of stars. Join us as we delve into the depths of space and unravel the wondrous stories of stellar creation that shape the fabric of the universe. In the vast expanse of the cosmos, stellar nurseries stand as celestial cradles where the intricate process of star formation unfolds. These cosmic regions, often found within vast clouds of gas and dust known as nebulae, serve as the fertile grounds from which stars emerge. Within these dense clouds, gravitational forces begin to exert their influence, pulling together pockets of gas and dust to form what are known as protostars, the embryonic stages of stars. The journey to stellar birth begins with the gravitational collapse of a molecular cloud, a vast reservoir of gas and dust that spans light years across. As regions of the molecular cloud become increasingly dense under the relentless pull of gravity, they become gravitationally unstable and begin to collapse in on themselves. This collapse triggers a cascade of events as the material within the cloud begins to heat up and condense, forming clumps and filaments that will eventually give rise to new stars. Within these collapsing clouds, protostars begin to take shape as gravity continues to compress the surrounding material. As the protostar grows in size and mass, its core temperature rises, eventually reaching temperatures high enough to ignite nuclear fusion, the process by which hydrogen atoms fuse together to form helium, releasing a tremendous amount of energy in the process. This marks the moment of stellar birth, as the protostar transitions into a fully fledged star, illuminating the surrounding nebula with its radiant glow. The process of star formation is a delicate dance between gravity and radiation, with each step governed by the laws of physics. As the protostar continues to accrete material from its surrounding disk, it becomes enveloped in a cocoon of gas and dust, shielding it from the harsh radiation of nearby stars. Over time, the protostar sheds its cocoon and emerges into the stellar nursery as a newborn star, its brilliance lighting up the surrounding nebula with its luminous glow. Stellar nurseries come in a variety of shapes and sizes, from compact stellar associations to sprawling giant molecular clouds. Some stellar nurseries are bustling hubs of activity, teeming with young stars and protostellar embryos, while others are quiet and serene, awaiting the gentle touch of gravity to spark the birth of new celestial beacons. Regardless of their size or composition, stellar nurseries play a crucial role in the cosmic cycle of birth and death, shaping the destiny of stars and galaxies across the universe. As we peer into the depths of these stellar nurseries, we are witnessing the genesis of cosmic wonders, the birth of stars that will light up the night sky for billions of years to come. Join us on our journey through the cosmos as we unravel the mysteries of stellar birth and explore the wonders hidden within the depths of space and time. The birth of a star marks a pivotal moment in the cosmic narrative, as gravity triumphs over the forces of inertia and triggers the ignition of nuclear fusion within the core of a protostar. As the protostar continues to accrete mass from its surrounding disk of gas and dust, its core temperature steadily rises, reaching critical levels where nuclear fusion reactions can occur. This transformative process unleashes a torrent of energy as hydrogen atoms fuse together to form helium, releasing an immense amount of heat and light in the process. The onset of nuclear fusion heralds the birth of a star, as it begins to shine with the brilliance of 1,000 suns, illuminating the surrounding stellar nursery with its radiant glow. This momentous event marks the transition from the protostellar phase to the main sequence phase of stellar evolution, where the newly formed star settles into a stable equilibrium state and begins its journey through the cosmic expanse. From this point onward, the star will burn steadily for millions or even billions of years, transforming hydrogen into helium in its core and radiating energy into space. The process of nuclear fusion within a star's core is a delicate balancing act between gravity, which seeks to compress the star's core, and radiation pressure, which pushes outward against the force of gravity. In stars like our Sun, this delicate balance is maintained by the energy released from nuclear fusion, which generates outward pressure that counteracts the inward pull of gravity. This equilibrium state allows the star to remain stable for billions of years, shining brightly in the cosmic tapestry as it fuses hydrogen into helium in its core. As the star continues to burn through its nuclear fuel, it undergoes a gradual process of evolution, transforming from a young, luminous main-sequence star into a mature, stable giant or supergiant star. During this phase of stellar evolution, the star's core temperature increases, triggering additional nuclear reactions that produce heavier elements like carbon, oxygen, and iron. Eventually, the star exhausts its nuclear fuel and begins to run out of energy, setting the stage for the final chapters of its cosmic journey. The birth of a star is not only a momentous event in the life of the universe, but also a catalyst for the formation of planetary systems and the emergence of life itself. As stars shine brightly in the night sky, they illuminate the surrounding regions of space, providing the energy necessary for the formation of planets and the synthesis of complex organic molecules. In this way, stars serve as the cosmic architects of life, shaping the conditions necessary for the emergence of life forms across the universe. After their spectacular birth, stars embark on a captivating journey of evolution, undergoing transformative changes as they age. The fate of a star is determined primarily by its mass, with high-mass stars experiencing vastly different evolutionary paths than their low-mass counterparts. For stars like our Sun, the journey begins on the main sequence, a stable phase of stellar evolution characterized by the fusion of hydrogen into helium in the star's core. As a star ages and exhausts its hydrogen fuel, it begins to undergo subtle changes that herald the next phase of its evolution. For low-mass stars like our Sun, this process occurs gradually over billions of years. As the star swells into a red giant, its outer layers expanding outward and engulfing nearby planets. Meanwhile, in the core of the star, helium fusion begins to take place, producing heavier elements like carbon and oxygen and generating the energy necessary to support the star against gravitational collapse. For high-mass stars, the journey through stellar evolution is far more dramatic and short-lived. These massive celestial behemoths burn through their nuclear fuel at a rapid pace, exhausting their hydrogen supply in a fraction of the time it takes for low-mass stars. As a result, high-mass stars undergo a series of explosive events, culminating in a spectacular supernova explosion that scatters heavy elements forged in the star's core throughout the surrounding interstellar medium. Following a supernova explosion, the fate of a high-mass star depends on the mass of its core. For stars with cores less than about 3 times the mass of the Sun, the core collapses into a dense neutron star, while for more massive cores, the collapse continues unabated, resulting in the formation of a black hole. These exotic remnants of stellar death are among the most enigmatic objects in the universe, with properties that challenge our understanding of the fundamental laws of physics. As the remnants of a supernova explosion disperse into the interstellar medium, they enrich the surrounding regions of space with heavy elements like iron, carbon, and oxygen, the raw materials necessary for the formation of new stars and planetary systems. In this way, the death of a star gives rise to new cosmic beginnings, as the cycle of stellar birth and death continues unabated across the vast expanse of the universe. Stars rarely form in isolation. Instead, they often emerge in clusters, bound together by the gravitational forces that shape the cosmic landscape. These stellar families, known as star clusters, come in a variety of shapes and sizes, ranging from compact open clusters to sprawling globular clusters that orbit the centers of galaxies. Within these clusters, hundreds or even thousands of stars are born from the same stellar nursery, sharing a common origin and destiny as they journey through the cosmos. One of the most remarkable aspects of the star clusters is their diversity in age and composition. Open clusters, for example, are relatively young and contain stars that formed from the same molecular cloud within the last few million years. These dynamic stellar nurseries are characterized by their rich tapestry of young stars, many of which are still surrounded by the remnants of their birth clouds, such as protoplanetary disks and Herbig-Haro objects. In contrast, globular clusters are ancient cosmic relics that date back to the early days of the universe. These dense agglomerations of stars, which can contain hundreds of thousands or even millions of members, orbit the centers of galaxies like satellites, forming vast halos that stretch across the galactic landscape. Within these ancient star cities, stars are packed together in a tight embrace, their gravitational interactions giving rise to dynamic phenomena like stellar collisions and close encounters. Despite their differences in age and composition, star clusters share a common origin and evolution shaped by the gravitational forces that bind them together. Over time, the stars within a cluster drift apart as a result of gravitational interactions with other stars and external forces like galactic tides. Eventually, the cluster disperses entirely, its stars scattering across the galaxy to join the stellar population at large. The study of star clusters offers valuable insights into the process of stellar birth and evolution, as well as the dynamics of galactic structure and formation. By analyzing the properties of star clusters, such as their age, composition, and spatial distribution, astronomers can unravel the mysteries of cosmic history and trace the origins of stars and galaxies back to their primordial beginnings. The legacy of stars extends far beyond their lifetimes, shaping the very fabric of the cosmos and providing the building blocks for the emergence of new cosmic wonders. One of the most profound ways in which stars leave their mark on the universe is through the process of nucleosynthesis, the production of heavy elements within their cores. During their lifetimes, stars fuse lighter elements like hydrogen and helium into heavier elements like carbon, oxygen, and iron, generating the diverse array of elements that populate the periodic table. The culmination of this process occurs during the explosive deaths of massive stars in supernova explosions, where the intense temperatures and pressures within the star's core trigger a rapid series of nuclear reactions. These cataclysmic events scatter heavy elements forged in the core of the star throughout the surrounding interstellar medium, enriching the cosmos with the raw materials necessary for the formation of new stars, planets, and even life itself. In addition to shaping the chemical composition of the cosmos, the death of a massive star in a supernova explosion can also trigger the formation of exotic remnants like neutron stars and black holes. Neutron stars, which form when the core of a massive star collapses under its own gravity, are among the densest objects in the universe, with a mass comparable to that of the Sun compressed into a sphere just a few kilometers across. Black holes, on the other hand, are even more enigmatic, with gravity so intense that not even light can escape their grasp. The remnants of supernova explosions continue to exert a profound influence on the surrounding regions of space long after the initial explosion has faded from view. As the debris from a supernova disperses into the interstellar medium, it triggers the formation of new stars and planetary systems, enriching the cosmic landscape with the raw materials necessary for the emergence of life. In this way, the death of a star gives rise to new cosmic beginnings. As the cycle of stellar birth and death continues unabated across the vast expanse of the universe, stars also play a crucial role in shaping the dynamics of galaxies and the evolution of cosmic structures. As stars move through their life cycles, they exert gravitational influences on one another, forming dynamic systems like stellar clusters and spiral arms within galaxies. Over time, these gravitational interactions give rise to complex structures like galaxy clusters and superclusters, which serve as the building blocks of the cosmic web that spans the universe. As we conclude our cosmic journey through the stories of stellar birth, we are left in awe of the intricate dance of gravity, gas, and radiation that shapes the destiny of stars. Join us next time on The Cosmic Commute as we continue to explore the wonders of the universe and uncover the mysteries hidden within the depths of space and time. Until then, keep looking up, fellow cosmic travelers.